Hello everyone, this is Nur Imtiazul Haq. I am from Department of Electrical and Computer Engineering of Florida International University. So today I am going to present our paper naming Ensemble-based efficient anomaly detection for smart building control system that has been recently accepted in IEEE COMPSAC 2021. So this is the outline of my presentation. At first, I will summarize our work, then a short overview of the smart building HVAC control system will be provided. After that, I'll be talking a bit about the current state-of-the-art intrusion detection system in a smart building HVAC control system. Then I'll be talking a bit about the main contributions of our work, followed by talking about the attack model that we have considered for our proposed intrusion detection system. After that, I will talk a bit about the key idea of our work. Then I will talk about the proposed model in a flow diagram. Then I'll evaluate our work based on the state-of-the-art dataset, naming commercial occupancy dataset, followed by concluding my presentation. So modern smart building control systems basically integrates the Internet of Things, which has enabled it to real-time monitor the demands and manage the heating, ventilation, and air conditioning systems more efficiently. But it has in terms increased the attack surface as well, which has made the adversarial alteration a very big concern. So in our work, we basically consider two major attack goals. One is the disruption of occupants' comfort, another one is increasing the energy consumption of HVAC control system. So to deal with the adversarial alteration, existing building control system are using a lot of state-of-the-art intrusion detection systems, but these tools they are using are either demonstrating high false alarm rate, or they are failing to detect anomalies, which actually puts the HVAC control system or the building occupants in a very vulnerable condition. So this in this paper we are proposing a novel IDS merging two unsupervised machine learning techniques, naming the autoencoder and one-class support vector machine, for identifying the abnormality in the smart building sensor measurements. So our proposed ensembled autoencoder one-class SVM model combines both models' benefit, which results in significant reduction of false positive and false negative rates as well, compared to the existing state-of-the-art IDSs. So we evaluate our proposed intrusion detection system on commercial occupancy dataset, which is a state-of-the-art dataset, and we found that our proposed IDS can achieve 99.6% F1. So the core components of HVAC control are the air handling unit, the fans, the vents, the indoor air quality monitor, the controller, and the anomaly detector. So the air handling unit basically is responsible for pushing and getting back the airs from each zone of a building. So a zone is comprised of several rooms. So air handling unit has some core components like this heating and cooling coils, the humidifier and the dehumidifier, the supply fan, and also the return fan. So the supply fan supplies air to in the room through the supply vents and gives back the air to the return vents. So the occupants are the main source of carbon dioxide and the heat generation. So also all these sensor measurements and the actuations are being controlled in a operation control and monitoring room, where there is a supervisory control and data acquisition system, and the data are being stored in a cloud or a server. And there is also a controller that actually takes all the sensor measurements from the building sensors and based on the sensor measurements it takes the control actions, and based on the control actions the actuators like the supply fans and also like the supply fans are actuated. So these are the state-of-the-art researches, like Pon et al. Proposed a context-aware building automation and control network data structure-based IDS which does not perform well for reducing false alarm rates. Liu et al. Proposed a lightweight rule-based intrusion detection system framework for a smart building control system. Liu et al. Proposed a long short-term memory-based control system for industrial climate control. Gardner et al. Applied an OCSVM-based novelty detection framework for detecting intracranial EEG seizures. Joy Kumar et al. Proposed an unsupervised learning strategy for multimodal sensor data anomaly detection. Malhotra et al. Proposed a LSTM network for encoder-decoder scheme for anomaly detection. But the main, as I said earlier, the main problems of these works are that they do not perform very much well for false positive alarms, and also they do not actually perform very well for zero-day attack detection. So these are the main contributions of our work. We mathematically modeled the smart building HVAC control system and generated attack dataset considering the stealthy false data injection attacks. So we proposed an intrusion detection system based on the ensemble of OCSVM and autoencoder techniques for efficient detection of corrupted or tempered data in smart building HVAC control systems. We extensively evaluated the performance of our proposed intrusion detection system and compared its performance with non-ensemble-based intrusion detection systems. The proposed IDS, and it is trained on benign samples only, but it shows significant performance in case of zero-day attack and shows good performance for false anomaly and false benign sample detection. So this is the attack model. So we considered that the building entrance is exceptionally secure through the biometric sensors, and the controllers get alarmed while experiencing the inconsistency in occupant count through the zones. The total number of occupants in a zone should not exceed the maximum zone capacity. Also considered the controller security system verifies the current time slot sensor and actuator measurements with the past measurements. The attacker can sniff all the sensor measurements throughout the day and calculate corresponding actuation measurements using the knowledge about the HVAC control model. The attack model also considers the attacker's knowledge, accessibility, and capabilities to launch an attack. So these are the key ideas of our work. In our work, we have used both OCSVM model and autoencoder model. So the one class support vector machine model basically separates the train pattern from the origin using a decision boundary. So it's almost similar to support vector machines model, but here we have only the positive samples, no anomaly or the negative samples are there. The model's decision boundary can be modified by tuning to hyperparameters, naming gamma and nu. On the other hand, the autoencoder based machine learning model is basically a neural network model which basically regenerates the features of the model. So in the autoencoder model, the number of nodes in the hidden layer in the encoder portion should be less than the number of nodes in the previous layer, and the opposite is for the decoder portion. So the maximum deviation between the input sensor measurements and the reconstructed measurements is termed as the reconstruction error, and this error of the model is used to detect the anomalies. So the OCSVM model's hyperparameters are tuned in such a way that it comes up with a narrow boundary, but the problem is it outcomes more false alarm. The autoencoder model, on the other hand, produces more flexible boundary that misses alarms. So our key idea is to actually merge both the ideas. So one thing is that the OCSVM model's hyperparameter can be tuned to come up with flexible boundaries, but in that case it seems that it actually misses some specific dense regions, which we will be actually seeing in the next slides. This is the flow diagram of the proposed model. At first, the OCSVM model and the autoencoder model are being trained on the B9 dataset. Then the threshold of the autoencoder model is calculated based on the maximum reconstruction error of the training patterns. After that, the weight and the prediction of both the autoencoder model and the OCSVM models are being calculated on a sample to which we are actually using to determine whether it is a anomalous sample or a binary sample. So the prediction of the autoencoder model is basically the difference between the maximum reconstruction error threshold and the reconstruction error for the current sample. And the weight of the autoencoder model is basically the deviation between these two. The prediction of the OCSVM model is basically determined whether the sample is out of the boundary or inside the boundary. If it is outside the boundary, then it is considered as an anomalous sample. The weight of the OCSVM model is basically the distance from the boundary to the sample. And after that, to actually make it comparable, both of the weights of the autoencoder and the OCSVM models are being normalized. Then the weight sample is basically calculated by the sum of product of the weight and prediction of the autoencoder and the OCSVM models. And based on this weight sample, the prediction for the sample is being provided, and this is our proposed model. So these are the evaluations. So at first, let's see the learned boundary or the frontier of the OCSVM model, and you can see that the learned boundary of the OCSVM model has misses some training patterns. So we basically use the gamma value to be 0.03 and the no value to be 0.003 in this case, after a lot of experimentation, and we found this to be the optimal boundary. We can alter the hyperparameter in such a way so that we can come up with more flexible boundary, but in that case, as we said earlier, this OCSVM model basically misses these dense regions. So that's why we are actually ensembling both the OCSVM model and the autoencoder model. So after ensembling, like the way we proposed, we can see that the ensembled model can come up with like some very good results, and both of the models can find the true binaries and the true anomalies very effectively, and they actually produces very less false benign and the false anomalies in case of like no person restriction and 1, 3 or 5% restrictions. So in the case of 5 and 3% restriction, we can see that the number of false benign and the false anomalies are exceptionally low, but in case of 1% restriction, it is very hard to actually figure out this alteration. But the good part is that although there are like a significantly high amount of false anomaly and false benign, this 1% alteration does not actually can actually meet the attacker's goal significantly, like this occupants comfort or the energy consumption or the cost increment attacks. So if we see the performance comparison between the proposed IDS and the individual IDS models, so you can see that the proposed IDS always comes up with high accuracy, precision and F1 score compared to the individual IDS models in case of both cost increment and the comfort disruption attacks. So in conclusion, I'll say that the smart building control system is becoming more vulnerable day by day due to novel cyber attacks, and are posing health and economic concern for building occupants. In this work, we proposed a novel ensemble learning model combining both autoencoder and OCSVM, and generated attack samples for evaluating our IDS, considering cost increment and cost disruption, comfort disruption based stealthy false data injection attacks, and experimented our proposed IDS on the commercial occupancy dataset, a state-of-the-art dataset, and shows that the ensemble learning model provides a significant performance boost and provides up to like 99.6% F1 score. In our future works, we'll explore the ensemble technique with other unsupervised model approaches for better novelty detection, and also for the hyperparameter optimization, we'll be using some kind of optimization approaches instead of manually tuning the hyperparameters.